All right, welcome. Today we are diving into something that's, well, kind of like a silent hero in modern computers, memory barriers. Think of them as these invisible traffic cops living right inside your CPU. They're the unseen guardians that literally stop our multi-core world from descending into total chaos. Seriously, without them, our systems would just be a swamp of corrupted data and random crashes.
Okay, so to kick things off, let's start with a little puzzle. We're going to look at a piece of code that honestly seems perfectly fine on the surface. It's simple, it looks logical, but it's hiding a ticking time bomb. A really critical bug that only rears its ugly head when you have more than one CPU in the mix.
So here it is. Take a look. This function, what's it do? Well, it grabs some memory, it sets two fields, A and B, and then, this is the key part, it makes a global pointer, GP, point to that new memory. Super simple, right? I mean, what could possibly go wrong? The idea is that some other part of the system is going to use that global pointer, GP, to read the data. Now the problem, well, it's all about the order of things, but maybe not in the way you'd first guess.
All right, so to crack this puzzle, we have to understand a really fundamental truth about modern computers. And that is, they are absolute, relentless optimizers. I mean, both the compiler, the thing that turns your code into machine instructions, and the CPU itself will do just about anything to be faster. And that, well, that's where the anarchy begins.
And this slide, this gets right to the heart of our problem. See, you write your code in what we call program order. It's a nice, clear, logical sequence of steps. But to squeeze out every last drop of performance, the compiler and the CPU can just shuffle those steps around into a totally different execution order. So in our example, they might look at the code and decide, hey, you know what? It's actually faster to set that global pointer first before we even bother writing the data it's supposed to point to.
And look, don't go thinking this is some weird exotic problem for obscure hardware that nobody uses. Nope. As this quote from the kernel documentation makes crystal clear, this affects pretty much everything. Even the x86 processors that are probably in your desktop or laptop right now, they do these kinds of reorderings. It's just a fundamental part of how modern hardware is designed.
So here's the really crucial point. On a single CPU, none of this matters. It's invisible. The final result is exactly the same, so who cares, right? But in a multi-core system, it is an absolute catastrophe. Imagine another CPU sees that global pointer, GP, get updated. It thinks, great, new data. It goes to read it, and what does it find? Uninitialized garbage. Why? Because from its point of view, those writes just haven't happened yet.
So, how do we, as programmers, fight back against this chaos? How do we tell these, over-eager optimizers to just calm down and do things in the order we told them to? Well, we use a special tool. We draw a line in the sand, and that line is called a memory barrier.
A memory barrier is, well, pretty much exactly what it sounds like. It's a special instruction that tells both the CPU and the compiler, hey, stop. Do not move any memory operations from before this point to after this point, period. It forces a strict, non-negotiable order. It guarantees that everything you did before the barrier is finished and visible to the whole system before anything after the barrier is even allowed to start.
The best way to think about it is like a traffic cop at a busy intersection. The barrier puts its hand up. All the traffic coming from one direction has to stop, completely. Once all those cars are through and the intersection is clear, only then does the cop wave the other direction through. It restores order where there would otherwise be a total pileup.
And in a massive complex system like the Linux kernel, you don't just have one type of traffic cop. You've got specialists for different situations. You have the full memory barrier, SMPMB, which is like the cop that stops all traffic in every direction. But then you have lighter weight versions, like SMP store release, which just makes sure all the writes, the stores, before it are done. Or SMP load acquire, which makes sure all the reads, the loads after it, have to wait. This gives you much finer control, which is way more efficient.
All right, so theory is great and all, but let's see how these guardians actually work out there in the wild. We're going to look at two real-world examples straight from the Linux kernel, and we'll start with a data structure you've probably seen a bunch of times.
So our first case study is the good old circular buffer. This is a classic way for one part of the system, we'll call it the producer, to pass data to another part, the consumer, without them constantly getting in each other's way. The best analogy really is a conveyor belt at a factory. Okay, now for this conveyor belt to work safely, the producer has to follow a very strict protocol. Step 1. It puts the new item, the new data, onto the belt. Step 2. And this is absolutely the most crucial part. It puts up a memory barrier. This is the guarantee that the data is actually on the belt before anything else happens. And only then, step 3, does it update the head pointer. That's like flipping the switch that moves the belt, telling the consumer, hey, new stuff is ready for you. Without that barrier, the consumer might get the signal before the item is even fully on the belt. Big mess.
All right, let's raise the stakes a bit. We're now moving on to a more high-stakes example, the kernel's read-copy-update mechanism, or RCU. Now this is a seriously sophisticated piece of engineering. It allows tons of CPUs to read data at the exact same time a writer is updating it, and it does it all without using traditional locks, which can really slow things down. It is incredibly fast, but its entire safety net, it all hangs on getting the memory ordering absolutely perfect.
This table lays out the whole disaster scenario, exactly what goes wrong without a barrier. So follow along here. On the left, you've got CPU 0, the writer. It decides to free an old piece of data. It waits for something called a grace period to make sure no one else is using it. But over on the right, on CPU 1, a reader is trying to access that very same data. Because of reordering, CPU 1 might access a piece of that data after CPU 0 has already finished its grace period and freed the memory. And the result? It's right there. Boom. A nasty system crash because it's trying to use memory that's already gone.
And this is where our hero comes in. The memory barrier, tucked away inside that RCU dereference function, saves the day. It provides an absolute ordering guarantee. It forces CPU 1 to finish its read of the pointer and the data it points to before the grace period over on CPU 0 is allowed to finish. This is how it ensures that a writer can never ever pull the rug out from under a reader. It's truly the linchpin holding the entire RCU system together.
So, as we've seen, these barriers are just everywhere in parallel code, even when you can't see them directly. They really are the quiet, unseen guardians that are constantly at work making our multi-core world safe and, predictable.
Okay, let's just quickly recap the big takeaways here. First, to be faster, your computer basically lies to you about the order it's doing things. Second, this reordering can create some of the most subtle, nightmarish bugs you can imagine in multi-threaded code. And third, memory barriers are the essential instructions we use to enforce order and bring back correctness. You could say they are the very foundation of safe parallel programming.
And hey, if all of this feels a little mind-bending, don't worry, you are in very good company. I love this quote from the kernel docs. It tells a story about how even the actual hardware architects who designed one of the first CPUs that did all this reordering, it took a good hour to convince one of the top kernel guys that barriers were even needed. And then it took him 2 hours to convince them their documentation was confusing. So yeah, these concepts are genuinely tricky, even for the experts who build this stuff.
So I'll leave you with this final thought to chew on. A multi-threaded program that seems to work but doesn't have the right memory barriers? Well, it isn't actually correct. It's just lucky. And as we all know, in the world of computing, luck always runs out. The question is your code correct, or is it just an accident waiting to happen? Thanks for joining me for this explainer.